They told you electricity has limits. Wires heat up, energy bleeds away. 5% of everything we generate just vanishes into thin air during transmission. But there is a state of matter where electrons move forever without losing a single joule. No friction, no resistance, zero. And the quantum rules that make it possible read like science fiction until you see them measured in a lab at minus 270 degrees Celsius. But here is what nobody talks about. We are closer to room temperature superconductors than we have ever been in history. December 2024, a team at the Max Planck Institute for Chemistry published direct measurements of hydrogen sulfide under crushing pressure, 203 Kelvin, that is minus 70 Celsius, warm enough that you could theoretically hold it in your bare hands if the megabar pressure did not instantly flatten you. The paper hit Nature on December 21st, 2025. Fengdu led the study. Mikhail Arametz, who died in November 2024, called it the most important work in hydride superconductivity since 2015. This is not theoretical anymore. This is measured, proven, real. Insane until you understand the numbers. Analyzing hydrogen-rich superconductors at megabar pressures, and the Max Planck Institute's direct tunneling spectroscopy measurements confirming electron pairing mechanisms in hydrogen sulfide. These are not generic science websites. These are peer-reviewed publications with experimental data showing superconducting gaps measured by quantum sensors inside diamond anvil cells at pressures exceeding 140 gigapascals. Now back to the information. This happens trillions of times per second in any normal conductor. But drop the temperature low enough in specific materials and something breaks. He runs current through a superconducting loop and it flows for years without decaying. No battery, no voltage, just perpetual motion at the quantum scale. He won the Nobel Prize in Physics in 1913, but he had no idea why it worked. They describe a mechanism so counterintuitive that even physicists struggle to accept it. Electrons repel each other. That is basic electrostatics, like charges push apart. But at low temperatures in certain materials, electrons pair up. They form bound states called Cooper pairs. And those pairs behave like bosons instead of fermions. That one change unlocks everything. Its negative charge pulls on the positive ions nearby. The lattice deforms, bends inward, creates a region of slightly higher positive charge density. That deformation persists for a fraction of a second. Another electron with opposite momentum and opposite spin senses that positive region and gets attracted to it. The two electrons become correlated through the lattice vibration. The phonon mediates the interaction. The binding energy is tiny, around 0.001 electron volts. Thermal energy at room temperature is about 0.026 electron volts. That is why Cooper pairs only form when you cool the material down. Heat breaks them apart. Exclusion principle. But Cooper pairs have integer spin. They act like bosons. They follow Bose-Einstein statistics. All of them drop into the ground state together. This is a macroscopic quantum phenomenon. Billions of electron pairs moving in perfect coherence. No scattering, no resistance, superconductivity. Below the critical temperature, thermal fluctuations are not strong enough to do it. The pairs stay intact. They move through the lattice without dissipating energy. The ratio of the energy gap to the critical temperature is a constant, 3.53 times the Boltzmann constant. This holds for most conventional superconductors. Tin has a ratio of 3.46. Lead is 4.29. The theory works. But BCS theory has limits. It predicts that conventional superconductors cannot exceed about 40 Kelvin. The mechanism depends on phonon energies, and those are capped by the atomic masses in the lattice. Heavier atoms vibrate slower. Lower phonon frequencies mean lower critical temperatures. For decades, the record stayed stuck at 23 Kelvin. Then, 1986 happened. Georg Bednorz and Karl Müller at IBM Zurich discover superconductivity in a ceramic. Lanthanum barium copper oxide, 35 Kelvin. That is above the BCS limit. They win the Nobel Prize in 1987. Paul Chu at the University of Houston pushes it further. Yttrium barium copper oxide, 90 Kelvin, above the boiling point of liquid nitrogen. Suddenly, you do not need liquid helium anymore. Liquid nitrogen is cheap, abundant. This is a game changer for applications. 40 years later, we still do not have a complete theory for high-temperature superconductivity in cuprates. The mystery drives thousands of experiments every year. Superconductivity at 203 Kelvin, minus 70 Celsius. This is a conventional superconductor. BCS theory applies. The phonons are hydrogen vibrations. Hydrogen is the lightest element. It vibrates fast. High phonon frequencies. Strong electron-phonon coupling. The coupling constant lambda is around 2. That is huge compared to typical metals where lambda is around 0.5. Combine that with the high frequency phonons and you get a critical temperature that smashes every previous record. Superconductivity emerges. Then 2019, lanthanum decahydride, 250 Kelvin, minus 23 Celsius, closer to room temperature than any material ever measured. The pressure is higher, around 170 gigapascals. The structure is similar, a metal atom surrounded by hydrogen cages. The hydrogen network conducts strong coupling, high phonon frequencies, the same mechanism as hydrogen sulfide but pushed further, published in Nature. Reproduced by multiple labs. This is real. Electrons tunnel across the barrier. The tunneling current depends on the density of states. In a superconductor, the density of states has a sharp peak at the edge of the gap. You can see it in the data. The gap is about 30 millielectron volts. The ratio to the critical temperature matches BCS predictions almost exactly. This confirms that hydrogen sulfide is a phonon-mediated superconductor. The pairing comes from lattice vibrations. Not spin, not charge fluctuations, phonons. Published in Nature. December the 21st, 2025. Mikhail Eremets, who passed away in November 2024, described this as the most important work in hydride superconductivity since the original discovery in 2015. Vasily Minkov, project leader at the Max Planck Institute, said it brings room temperature superconductivity at moderate pressures one step closer to reality. So what about room temperature at ambient pressure? That is the holy grail. October 2025, Penn State researchers publish a new computational approach in superconductor science and technology. Zhi-Kuei Liu leads the team. They combine density functional theory with BCS equations, DFT models, electron behavior. BCS describes pairing. Previously, these frameworks were treated separately. Liu connects them. The key insight is that even though DFT does not directly model Cooper pairs, the electron density it predicts should resemble that of paired electrons. This lets you screen materials computationally before synthesizing them. You calculate the electron density, check if it matches a superconducting state, predict the critical temperature, then make the material and test it. This could accelerate discovery by orders of magnitude. March 2025. Kostya Trochenko and Chris Pickard publish in Journal of Physics Condensed Matter. They calculate the upper limit of superconducting critical temperature based on fundamental constants. Electron mass, electron charge, Planck constant. These set the maximum phonon frequency a material can sustain. That frequency caps the critical temperature. The calculation gives an upper bound between 100 and 1000 Kelvin. Room temperature sits right in that range. This means room temperature superconductivity is not forbidden by the laws of physics. It is possible. We just need to find the right material. Nickelates are chemically similar to cuprates. Nickel sits next to copper on the periodic table. In 2019, the same team discovered superconductivity in nickel oxide compounds, but only under high pressure. The new work uses substrate strain. They grow a thin film of nickelate on a substrate that compresses it laterally. That compression mimics the effect of external pressure, but without needing a diamond anvil cell. The material stays superconducting at room pressure. The critical temperature is lower than under full pressure, about 15 Kelvin, but it is stable. You can study it with X-ray scattering, angle-resolved photoemission spectroscopy, techniques that do not work inside a diamond cell, published in Nature, December 19th, 2024. This opens up nickelates for detailed investigation. Understanding how they work could point the way to higher temperature versions. You can write a single wave function that describes all the pairs together. Break one pair and you change the energy of the entire system. That is why there is an energy gap. The gap is the energy cost to break the condensate. No voltage. This is the Josephson effect. Brian Josephson predicted it in 1962. He was 23 years old, a second-year graduate student at Cambridge. The current across the junction depends on the phase difference between the two superconductors. If you apply a voltage, the phase evolves in time. The current oscillates at a frequency proportional to the voltage. 2 millivolts gives about 1 gigahertz. This lets you convert voltage to frequency with absurd precision. Josephson junctions are used in voltage standards worldwide. This is Heisenberg uncertainty at the macroscopic scale, a circuit containing billions of electrons behaving like a single quantum particle. Barrier. They measure the escape rate as they lower the temperature. As expected, the rate drops, but below 50 millikelvin, it stops dropping. The rate stays constant. The system is tunneling through the barrier, not over it, through it. Macroscopic quantum tunneling. A centimeter-wide circuit behaving like a single quantum object penetrating a potential barrier. They use microwaves to control the system. The microwaves let them measure the energy levels, quantized, like an atom. This is the foundation of superconducting qubits. Clark, Deverett, and Martinis won the Nobel Prize in Physics in 2025 for this work. They cool tin and lead samples below the critical temperature in the presence of a magnetic field. The field inside the samples drops to nearly zero. The superconductor generates surface currents that create a magnetic field exactly opposite to the applied field. The two cancel inside the material. The field is expelled. This is not just perfect conductivity. A perfect conductor would prevent changes in magnetic flux. But a superconductor actively expels static fields. This is perfect diamagnetism. The currents persist forever because there is no resistance to decay them. This is why you can levitate a magnet above a superconductor. The expelled field pushes the magnet up. Stable levitation, quantum locking. Published in Nature, February 28, 2024. Nitrogen vacancy centers are quantum sensors. They detect magnetic fields with submicron resolution. The team applies a magnetic field to a sample of cerium hydride compressed to over 100 gigapascals. They cool it below the critical temperature. The nitrogen vacancy centers measure the local field. It drops. Diamagnetic response. Clear signature of the Meissner Effect. They also map spatial inhomogeneities. The superconducting regions are not uniform, micron scale variations. This matters for optimizing synthesis. You want homogeneous samples for applications. The quantum sensors let you see where the synthesis needs improvement. Maximum critical temperature is 25 Kelvin, low compared to other cup rates. Most of the family are good insulators, but the team finds something unexpected. Electron pairing occurs at much higher temperatures than superconductivity. The pairs form, but they do not condense into a superconducting state until you cool much lower. This is called a pseudo-gap phase. Pairs exist, but without phase coherence. No superconductivity. This suggests that pairing and condensation are separate processes. Understanding this could unlock higher temperature superconductivity in other materials. The team measures linear birefringence and linear dichroism. These reveal symmetry breaking in the crystal. The optical properties depend on the direction you shine light. This anisotropy is linked to the copper-oxygen planes where superconductivity happens. By understanding the symmetry, you can probe the pairing mechanism. The work shows that the pseudo-gap phase has different symmetry than the superconducting phase. This is a clue to what mediates pairing in cuprates, still unsolved after 40 years. The researchers measure resistivity under extreme magnetic fields. When the field exceeds the critical field, superconductivity breaks. The material returns to normal, but the transition is sharp, clean, reproducible. James Walsh at UMass Amherst says measuring resistivity under such high magnetic fields is impressive. The data confirms that lanthanum hydrides bridge the gap between conventional low-temperature superconductors and high-temperature cup rates. Understanding that bridge could reveal new pairing mechanisms. The interaction strength scales with the square of the displacement. This introduces quantum fluctuations of phonons, zero-point energy. Even at absolute zero, phonons fluctuate. Electrons interact with those quantum fluctuations. They form quantum bipolarons, pairs bound by quantum effects instead of classical lattice distortions. The calculation shows that strong quadratic coupling can enhance superconductivity. Critical temperatures could reach higher values than linear coupling allows. This is speculative. No material has demonstrated it yet. But the theory suggests a new route to room temperature superconductivity. Room temperature. The wrinkles form line defects, one-dimensional channels. Electrons confined to those channels exhibit pairing at room temperature. Vinokur-Valeri at Terra Quantum AG calls it an important pioneering step. The scientific community remains skeptical. Reproducibility is the issue. Other labs have not confirmed the results, but if valid, it points to a mechanism where defects and confinement enhance pairing. Graphite is cheap. Abundant. If you can engineer the defects reliably, you have a room temperature superconductor at ambient pressure. That would change everything. The original data had errors, not fraud, just mistakes. Science corrected itself. But it wasted months of effort. The lesson is clear. Extraordinary claims require extraordinary evidence, reproducibility, multiple labs, independent confirmation. Until then, treat it as preliminary. Electrical resistance drops to zero. Meissner effect observed, isotope effect confirmed. These are the three pillars of superconductivity, all present. The challenge is reducing the pressure. Can you stabilize the structure at ambient conditions? That is the question driving research today. Metal, hydrogen, nitrogen. Computational screening identifies candidates, then synthesis, then testing. It is slow, but progress is real. Every few years, a new record. 2015, 203 Kelvin. 2019, 250 Kelvin. What is next? 270 Kelvin, 290 Kelvin. Room temperature is 293 Kelvin. We are within striking distance. The applications are staggering. Power grids with zero transmission loss. The U.S. Energy Information Administration estimates 5% of electricity is lost in transmission. Superconducting cables eliminate that. Maglev trains that levitate on superconducting tracks. Frictionless, silent, fast. MRI machines with stronger magnetic fields, higher resolution imaging, particle accelerators with superconducting magnets. The Large Hadron Collider uses thousands of superconducting magnets cooled with liquid helium. Room temperature superconductors would eliminate the cooling infrastructure. Quantum computers with superconducting qubits, stable, scalable. Thomas Conte at Georgia Tech says the impact on computing would be profound. A superconductor that only works at 150 gigapascals is a laboratory curiosity. You cannot build a power grid with diamond anvil cells. You need ambient pressure, or at least moderate pressure. 10 gigapascals is manageable. 100 gigapascals is not. Researchers are working on it. Substrate strain, chemical substitution, nanostructuring. Ways to mimic the effect of pressure without applying it externally. April 2023. Brookhaven National Laboratory compares nickelates and cuprates using synchrotron X-rays. Both have magnetic interactions between metal and oxygen ions, but nickel interactions are slightly weaker than copper. The charge density wave is also stronger in nickelates. These differences might explain why nickelates have lower critical temperatures. Understanding the differences could point to ways to enhance nickelates. Make them more like cuprates, push the critical temperature higher. These are not small effects. These are macroscopic quantum phenomena visible to the naked eye when you levitate a magnet or measure zero resistance. The challenge is engineering, finding the right combination of elements and structure and pressure to achieve room temperature, superconductivity at ambient conditions. Map phase diagrams. Some will fail, some will succeed. Each success pushes the record higher, 260 Kelvin, 270 Kelvin, eventually room temperature. Lanthanum hydride on a compressed substrate, cerium hydride, yttrium hydride, see what happens. Josephson junctions, squid magnetometers. These let you probe superconductivity at the micron scale, map inhomogeneities, optimize synthesis, improve material quality. Better materials mean higher critical temperatures, more reproducibility, closer to applications. Phase locking across macroscopic distances. Magnetic field expulsion, zero resistance. These are the quantum rules that power superconductors. Strange, counterintuitive, but real. And we are learning to control them. The United States, competing to find the first room temperature ambient pressure superconductor. Billions in funding, thousands of researchers. The prize is enormous. Revolutionize energy, transportation, computing, medicine. Whoever gets there first rewrites the rules. That is how it works. Slow, methodical, but reliable. The hydrogen sulfide results from 2015 took months to confirm. Multiple labs, different techniques. All agreed. 203 Kelvin at 155 gigapascals. Real. Everything fits. The theory predicts. The experiment confirms. That is science working. Not even that hard compared to the jump from 23 Kelvin to 250 Kelvin. That was a factor of 10. This is less than 20%. The experimental techniques are improving. Diamond anvil cells with better pressure control. Quantum sensors with higher resolution. Synthesis methods that produce cleaner samples. Better data. More reliable. Less noise. Points to the next target. It is a question of when. The quantum rules are wild. Cooper pairs separated by hundreds of nanometers. Phase coherence across centimeters. Tunneling through barriers at macroscopic scales. Magnetic fields expelled by persistent surface currents. Energy gaps protecting the condensate from thermal fluctuations. These are not approximations. These are exact quantum mechanical effects measured to extraordinary precision in laboratories worldwide. And the beauty is that the rules are universal. They do not care what material you use. Hydrogen sulfide, lanthanum hydride, cuprates, nickelates. If you get the structure right and the temperature low enough and the coupling strong enough, Cooper pairs form, the condensate appears, superconductivity emerges, same physics, different materials. The elegance is stunning. Bardeen, Cooper, and Schrieffer won the Nobel in 1972. Their equations describe conventional superconductors perfectly. The energy gap, the critical temperature, the isotope effect, all derived from first principles. Quantum mechanics applied to many body systems. It is one of the triumphs of 20th century physics. 130 Kelvin in mercury, barium, calcium, copper oxide under pressure. BCS theory says this should not be possible. Phonons alone cannot explain it. Something else is happening. Spin fluctuations, charge density waves, magnetic interactions. We still do not have a complete answer. That is what makes it exciting. A 40-year-old mystery still driving research. Conventional, but pushed to the limit. Light hydrogen atoms, high-frequency vibrations, strong coupling, critical temperatures approaching room temperature. This is BCS on steroids. The mechanism is the same, the numbers are different. And those numbers change everything. The diamond anvil cells that create them are engineering marvels. Two diamonds pressed together, the tips converge, the pressure multiplies. You can reach megabar pressures in a volume the size of a grain of salt, but you cannot scale that up. You cannot build devices. You need ambient pressure. Defect engineering. One of these will work, or maybe something we have not thought of yet, but it will happen. The physics allows it, The computational tools predict it. The experimental methods can test it. It is just a matter of time. Millions of patients scanned every year. Particle accelerators use niobium tin, 17 Kelvin. The Large Hadron Collider has 1,200 dipole magnets, each one superconducting, generating 8 Tesla fields. Without superconductors, the LHC does not exist. Neither does the Higgs boson discovery. Quantum computers use aluminum or niobium Josephson junctions, cooled to millikelvin temperatures, coherence times measured in microseconds. Enough to run algorithms, enough to demonstrate quantum advantage in specific problems. Google, IBM, Microsoft, all using superconducting qubits. The market potential is trillions of dollars. The energy savings alone justify the research investment. The fundamental constants calculation in March 2025. Each one advances the field, each one brings us closer. That is chemistry, that is synthesis and characterization and optimization. And we are getting better at it. A miscalculation that leads somewhere interesting. You cannot plan serendipity, but you can create the conditions where it happens. Fund the research, train the scientists, build the tools, run the experiments, and wait. No doubt. And then the engineering starts. Scale up, optimize, manufacture, deploy. Applications follow, power grids first, then transportation, then computing, then everything else. Magnetic field expulsion through persistent surface currents. Zero resistance from the energy gap protecting the condensate. These are the rules. They work at 4 Kelvin, they work at 90 Kelvin, they work at 250 Kelvin, they will work at 293 Kelvin. The physics guarantees it. Measuring resistances, mapping phase diagrams, calculating structures, screening candidates, synthesizing compounds, testing properties, iterating, refining, improving, getting closer. Phonon frequencies shift. Critical temperature drops with heavier isotopes. Everything checks out, multiple labs confirm. Independent verification, the paper publishes, Nature, Science. Physical review letters, the news spreads, room temperature superconductor discovered, ambient pressure reproducible. We just have not found the right one yet. But we will, because every wild quantum rule that powers superconductors points to one conclusion. Room temperature, superconductivity is possible, and what is possible eventually becomes real. 155 gigapascals. The gap measured 30 millielectron volts at 203 Kelvin. The ratio matched BCS predictions. The isotope effect confirmed phonon mediation. This is the most direct proof yet that hydrogen-rich superconductors work exactly as theory predicts. Mikhail Arametz, who dedicated his career to this field and passed away just weeks before the paper published, called it the most important measurement since the original discovery in 2015. His collaborator Vasily Minkov said it brings the dream of practical room temperature, superconductivity within reach. The quantum rules work, the materials work. Now we push the boundaries until resistance disappears at temperatures you can touch. In conventional superconductors, the coherence length is around 40 nanometers. In cuprates, it drops to 2 nanometers. In hydrogen sulfide, the coherence length is intermediate, around 10 nanometers. This balance is critical. At the critical temperature, it diverges. The Meissner Effect vanishes. Each vortex is a normal core surrounded by circulating supercurrents. The vortices repel each other. They arrange in a triangular lattice, the Abrikosov lattice, named after Alexei Abrikosov, who predicted it in 1957. He won the Nobel Prize in 2003. Defects in the material trap vortices, grain boundaries, impurities. Strong pinning keeps vortices stationary, zero resistance even in the mixed state. In hydrogen sulfide, replacing hydrogen with deuterium reduces the critical temperature by about 15%, from 203 Kelvin to 172 Kelvin. This is a huge effect. The large isotope effect confirms that phonons are the primary pairing mechanism, no doubt. Higher pressure actually reduces it. The structure changes. The hydrogen cage compresses. The lattice stiffens. Phonon frequencies increase, but the density of states decreases. The coupling weakens. 155 gigapascals is the sweet spot. Density functional theory is not perfect, but it is getting better. Machine learning is helping. Sharp transition. Electron-phonon coupling, then rank them, synthesize the top candidates. SLAC nickelate work shows substrate strain stabilizes superconductivity at room pressure. Apply this to hydrides, early results promising. A material that superconducts at room temperature and ambient pressure. Once you have that, everything changes. Power grids become lossless. Maglev trains everywhere. Medical imaging leaps forward. Quantum computing reaches full potential. And the physics says it is possible, soon.